Welcome to qnawire.
Hello, this is Josh. We're looking at this problem. We have this reaction. Gamma produces two different muons. Okay, so what this question is asking is what is the minimum wavelength, or rather, maximum wavelength, meaning minimum energy of these photons to produce these particles. Now, the problem states that we need to work in terms of electron rest mass. So for a muon, the rest mass is equal to 207 times the rest mass of an electron, which is, as we discussed in previous problems, 0.511 MeV per c squared. Okay, and for a single muon, that's going to give us a value of 105.8 MeV per c squared. Now there's two muons, two photons, so one photon needs to supply that much energy. The other photon will supply the other amount of energy. Okay. So the minimum energy needed to make this muon is 105.8 MeV, but they come as a pair. We'll just look at one. All right. So let's look at the energy. Energy of the gamma is equal to HF, which is Einstein's expression for energy of a photon. Now let's write the frequency in terms of C and lambda. All right, so frequency is equal to C over lambda. We're dealing with photons, it's always C. All right, let's plug that into our expression. So E, the energy of the photon, is equal to H times F, which is now C over lambda. All right, this term Hc, if you use Planck's constant in modern units, meaning eV times second, and you multiply that by your speed of light here, what you get for the value of Hc, which is very useful, especially for exams, is 1240 electron volt times nanometer. All right, now what does this mean? H is in units of what? eV times second, and C is in units of meters per second. All right, so the seconds cancel out of this, and the unit on meters is times 10 to the minus 9, which is nanometer. Okay, so when we plug in everything for our expression here, I can solve this for lambda, of course, and I'll get that lambda, and this is lambda max, the maximum. Realize that as the wavelength increases, the energy goes down. So largest wavelength means least amount of energy, and I will get that that is equal to Hc divided by E gamma. Okay, and when I solve this, what I get is that is equal to 1.172 times 10 to the minus 5 nanometer. Now nanometer is times 10 to the minus 9, so minus 9 minus 5. This is then equal to 1.172 times 10 to the minus 1/4. All right, now this question basically says, what speed are the muons moving if you have this wavelength for the photons? All right, for the minimum case, all the energy that the photons require is used to produce the muons. So for this wavelength, the velocity of the muons is equal to 0. There's no kinetic energy. K equals 0 because all the energy supplied by your photons was converted into just creating these particles. All right, if we need to make some space, we'll erase at the top. Now, this problem asks All right, if the wavelength of those photons is now half that maximum wavelength, what speed do the muons come out of that collision with? So, all right, let's go ahead and look at this. So my lambda now is equal to lambda max over 2. All right. So looking at my energy equation, E gamma equal HC over lambda max over 2. All right, basically what's going to happen then is lambda max over 2. I get that it's equal to 2 times HC divided by lambda max, which means that for this reaction, my gamma energy is equal to twice, let's put this as E gamma naught, the original energy. So that energy then is equal to 211.6 MeV per C squared. Or as we can see, it's just twice as much as the original one. Okay, now I am going to go ahead and make some room up here, so you can simply just, you can rewatch the front part if you need to look at this again, no problem there. All right, so when we're dealing with the energy of a particle, we need to handle relativistic effects, all right? So let's just clear out just a little bit more of a spot. Okay, a little bit of blobs in there, but that should be just fine. All right. So what's happening then is the energy of a particle is equal to, now I'm going to use this term gamma. Realize that this is not a photon times rest mass. It's difficult to avoid confusion at this point, but what we're going to do is my term gamma now is in this expression is how we're going to handle the relativistic correction for speed. All right. Okay. So gamma here is equal to 1 over the square root of 1 minus u squared over c squared, where u is the speed of the particle, which is what we want to deal with. Realize that this is the energy of the muon now. All right, what's been given to the muons? So I'm going to solve this expression for u. All right, what we need to realize is that this side here, E is equal to 2 times the rest mass, because rest mass was 105, and we have a quantity that's twice that. So our energy is 2 times rest mass, and that's equal to gamma times, whoops, wow, what a freak out. Okay, that is times 2e naught gamma, and then times what? Rest mass. So what we see here is that we have the expression where 2 equals gamma, all right? So what we need to do is I need to set the 1 over root 1 minus u squared over c squared equal to 2, and then solve that expression for u, and that will give us an idea of the velocity. All right. So all we're doing now is simply an algebra problem. That's all the physics we need. But let's go ahead and step through that algebra a little bit at a time. Okay. All right. So 2 equals 1 divided by the square root of 1 minus u squared over c squared. This quantity u squared over c squared is oftentimes seen as beta, another Greek letter. Everything in physics uses Greek letters. I'm not sure why. Okay, so let's go ahead and do some rearranging. I can multiply both sides by this radical and divide both sides by 2. So I will get that square root of 1 minus u squared over c squared equals 1/2. All right. And basically, putting through the rest of my algebra, I'm going to get this expression here. And I apologize for the time clearing this. This takes just one moment. All right, let's go ahead and think about this. So after doing some algebra, I will get that u is equal to the square root of 1 minus 1/4 times c, or 0.86 times c. So the muon's going 86% times the speed of light. All right, so which is quite significant. And if we put that in, I get that is 2.68 times 10 to the positive 8 meters per second. So each muon exits this reaction at this speed. All right, thanks.